Hi dear students. So in the last class we have discussed about the series combination and the equivalent resistance in the series combination, as well two more important things, that is the current value which is passing through each resistors in serial combination or series combination is equal. Okay, but the potential drop across each resistor will be varying, okay, according to the value of the resistance of the individual resistors. So we have seen that, and the equivalent resistance in the series combination, suppose if you are having three resistors as R1, R2 and R3, and if you are connecting them in series combination, then the equivalent resistance in series combination that we can take as RS. Okay, RS will be is equal to the total sum of the individual resistors, isn't it? R1 plus R2 plus R3. Okay, now let us come to the parallel combination or parallel connection. We can compare the parallel connection with the series connection. In the series connection, we have connected the resistors in end to end, isn't it? We have connected the resistors end to end, R1, R2 and R3. But here in this case, in the parallel combination, one end of the or one terminal of each resistor is connected at one junction. Okay, and the remaining or other terminals of the resistors is connected at the other junction. So you can see the resistors R1, R2 and R3 here are connected parallelly, and the terminals are connected at two different various junctions. Okay, now so that's why it is known as the parallel combination. Regarding the potential and the current value, in parallel combination, the potential drop across each resistor will be the same, because the three resistors are connected parallelly. Okay, so the potential drop across each resistor will be equal only. So at R1 it will be V. The potential drop across R2 also will be V, and R3 will be V. Okay, but now let us come to the current value. So potential is a constant in the case of parallel connection, or equal in the case of parallel connection, but in the case of series connection, the potential drop across the resistors was different, isn't it? The potential drop across the resistors were different, but the current value were same. Current value were the same. But here in the parallel combination of resistors, the current value will be different. At that time, the potential drop across the resistors will be the same. Now let us discuss about the current value. Actually, the current, consider the total current, it is I which is reaching at the junction K, reached at K. But afterwards, what will happen? The current will split into 3. Okay, the current value will split into 3 as well. If it is voltmeter connected, it will split into the 4, but we are not considering the voltmeter now. Okay, just consider the 3 resistors. Okay, the current will be splitted into 3 as through R1 it is I1, R2 it is I2, and R3 it is I3. Okay, so at a junction, three resistors. Okay, three resistors it is connected. So here it is R1, R2 and R3. So the current value will be I1, I2 and I3. Now come to the important point. That is the sum of the current value which is passing through the individual resistors will be equal to the total current in the circuit. That is, if the current value which is passing through individual resistors are I1, I2 and I3, if we are taking the sum, which will be is equal to the total current which is passing through the circuit, that is I. But in the case of that series combination, we have discussed that the potential drop across, we have to take the sum of the potential drop across each individual resistors, and that sum will be equal to the total potential or total applied potential from the cell. We have discussed that one. Now I1 plus I2 plus I3 is equal to I. That is the current which is passing through the individual resistors. If you are taking the sum of the current which is passing through the individual resistors, that will be equal to the total current which is passing through the circuit I. Okay, now let us come to, so these are the major things that you have to remember about the resistors in parallel connection. Now you have to come to let us go to the derivation of the equivalent resistance. We have to find out the equivalent resistance. Equivalent resistance in the sense the total resistance or total effective resistance which is in between this X and Y. Okay, this X and Y. The total resistance due to the R1, R2 and R3 and its parallel combination. We are going to see that one. Okay, so as we discussed all those things, in the parallel combination, the total current flowing will be is equal to the current which is the sum of the current which is passing through the each branch of the combination or each resistors or individual resistors. Now you have to use the Ohm's law. If the equivalent resistance you are considering as Rp, that is R parallel, okay, then if the total potential applied, if it is V, and the total current which is passing through the circuit, if it is I, then V by I will be is equal to Rp. Okay, so I will be is equal to V by Rp. So we have to substitute this V by Rp is equal to I in the equation, in this equation. The current I is equal to I1 plus I2 plus I3. The same way, I1 will be is equal to V by R1, because V by I is equal to, V by I1 is equal to R1. Okay, so I1 will be is equal to V by R1, I2 will be is equal to V by R2, I3 will be is equal to V by R3. So we are substituting that values. So I, that is equal to V by Rp. So I is equal to V by R1 is I1 plus I2 plus I3. Okay, now we are having V by Rp is equal to V by R1 plus V by R2 plus V by R3. So we are taking outside the V value. So V into 1 by R1 plus 1 by R2 plus 1 by R3, which is equal to V by Rp, where V will cancel. So the remaining will be 1 by Rp, that is the equivalent resistance in parallel combination Rp. So 1 by Rp will be is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So the equivalent resistance 1 by Rp, Okay, 1 upon the equivalent resistance of the parallel combination will be is equal to 1 upon the individual the sum of the one by R1, 1 by R2 and 1 by R3. If you are having n number of resistors, then it will be 1 by R1 plus 1 by R2 plus etc. up to 1 by Rn. In such a way you are finding out the equivalent resistance in the case of parallel combination. And this is actually the 1 by Rp value. If you want to find out the Rp value, Rp will be is equal to, you have to take the inverse of these values, isn't it? So we have to first of all add this one, then you have to add that one with this one, and then you should take the inverse. Okay, if you are adding this to the first two, it will be R1 plus R2 divided by R1 R2, okay, plus 1 by R3 will be there, that is R1 plus R2 plus R3 divided by R1 R2 R3 will be there. Inverse will be R1 R2 R3 divided by R1 plus R2 plus R3. Just check that one. Okay, just check the add this fractional numbers and just check whether it is right or not. Okay, okay, now let us come to the heating effect of the electric current. Suppose if you are using the television for a long time, and if you are after turning off this television, okay, if you are touching on the back side, you can see that the body of the television is little bit heated up. Otherwise, if you are using the ceiling fan for a long time, and after a few time, if you are turning it off, and if you are touching the motor portion of the ceiling fan, you can see that it is highly heated up, that portion. So actually in the ceiling fan, what is happening? The electrical energy is getting into the mechanical energy, or converted to the mechanical energy. But whenever the excess electric energy is reached over there in the fan, actually that is excess, the fan does not need that energy, then that energy will be converted into the form of heat energy. Okay, so that is one of the common or a very known example for the heating effect of the electric current. As well, this heating effect is used up in the heating coils, as well the electric iron. In all cases we are using the benefit of this heating effect. So if the electric circuit is purely resistive, there is a configuration of resistors only connected to a battery. The source energy continuously gets dissipated entirely in the form of heat. This is known as the heating effect. So suppose if we are considering the electric iron, in that one you know that the tungsten or nichrome wires are using, the resistance is very high, and then the electrical energy cannot pass through it. Okay, the current will not be passed smoothly through that particular materials. We cannot say them as conductors. They are not conductors as well, they are not insulators, but still they have the ability to conduct the electricity. Okay, their resistance is very high, so this electrical energy will be converted into some other form. Okay, so the current cannot flow smoothly, then there will be a kind of retarding force is there, so the energy loss should be happen over there. Energy should be converted into some other form. The current energy should converted into some other form, that is the heat. It is converted into the heat energy. Okay, so that is actually the heating effect of the current. The current energy or electrical energy is converting into the heat energy if the path which through the current is passing is having higher resistance. Okay, so considering a current I flowing through a resistor of resistance R, the difference, the potential difference across the resistance, if it is V, and T is the time for which the current is passed through the conductor, or the during which a charge Q flows across. Okay, so the charge Q flows through the resistor within a time of T, so I will be is equal to Q by T. Then the work done will be, so we know that the potential V is equal to the work by the charge, work done by charge. So work done will be is equal to V into Q. Okay, V into Q will be the work done. So if the work is happening, that means the source is giving some energy, so work into time will be the energy. Sorry, work no, we have to find out the power value. Sorry, power value. The power is actually the work by time. Work by time, it is power. So work, it is, we have already found that work is equal to V into Q. So V into Q by T will be the power. Okay, the power, it is V into Q by T. So that is the work done per time. So Q into V by T will be is equal to V into Q by T, which is equal to Q by T is equal to I. So the equation will be V into I. So the work done is equal to V into Q, and the power will be is equal to V into I. Okay, where V is the potential difference between the end of the terminals of the resistors, I is the current which is passing through the resistor, T is the time taken for Q amount of charge through pass through the resistor. So VI is the power. Now, so power value you are having, power into time will be is equal to the energy. The power into time will be is equal to energy. So VI into T, VI is the power, VI into T will be is equal to the energy, that is the energy is dissipated in the form of heat energy. So heat energy is equal to V into I into T. Now you can use the Ohm's law, that is R is equal to V by I. Then V will be is equal to I into R. So instead of this V in this equation, you have to use the I into R term. So I into, then H will be is equal to, instead of V you will write IR, V into, that is V, IR is equal to V, I into So which will be is equal to H. So I into I will be I square. So I square into R into T will be the other equation. So this is known as the Joule's law of heating. H is equal to I square RT is the Joule's law of heating, which is happening in the conductors which are having higher resistance. Okay. Then the current energy will be heated in, converted into the heat energy, or the heat dissipation will be taking place, and that amount of heat energy will be given by V into I into T or I square RT. So the heat produced in resistors will be directly proportional to the square of the current of a given resistance. For a given resistance value, the heat energy is directly proportional to the I square, that is the square of the current. Now, directly proportional to the resistance for a given current. For a given current value, it is directly proportional. That is, for a constant current value, which is directly proportional to the resistance and directly proportional to the time for which the current flows through the resistor. And if the time increases, then also the H value will increase. So the heat dissipation or the heat energy dissipated during the passing of current through a conductor which is having higher resistance at constant resistance. If the resistance value is not varying, then it which is heat energy dissipated will be directly proportional to the square of the current. Okay. And as well, if the current value is fixed, then it will be directly proportional to the resistance, and all the time which is directly proportional to the time with which, or the time duration for which the current is passing through the conductor. So these are the major points that you have to study and remember regarding the heating effect of the current. Okay, so we will wind up here, and in between we have missed some example questions. We will discuss that during the revision time. Okay, revision time means for this midsem examination we will be having a revision time. During that time we will discuss that example questions, and again we will refresh the theory portions with the help of that example questions. Okay, then thank you, wish you have a good day.